Okay, so let's start the next session, or next part of the session. Event selection in root is what we're talking about now. So it's building off of what Paul told you about in terms of using the deselectors and looking at our example channel of Omega production for selecting events. Okay, so what we need for event selection to determine how well we're doing is a sample of signal. So far you've all been looking at this BGGen background sample, this thing we call SIM1. And so this is a Pythia-based inclusive photo production generator. So it generates sort of all the background processes as well as our signal Omega channel. Mark Ito mentioned this in his talk, but this full sample is about 375 million events that we created. That's called the SIM1, and it's meant to match the spring 2016 data conditions. And that's roughly 6 hours of real beam time at the the higher rates we were running. So just to give you a sense of scale, and for this session, we'll just be using 1% of that sample to match the Omega signal sample we're using, which is 20,000 generated Omega events. Mike is going to talk about the generation of these and how you do that within the AmpTools classes. And so, yeah, this is about half an hour of the spring data is what we're using in using these two samples. So assume here, without knowing the details, that we're generating just single Omega events decaying to 3 pions, which have all the right linear polarization angular distributions. And we'll talk about more of that later. Okay, so those are the samples we're looking at. So let's start just with a quick sort of repeating what Paul was doing at the end of the last thing, where we're going to do. I'll be doing a few exercises sort of as we're going through. I'm much lazier than Paul, so I won't be creating any code on the fly, but we'll run through a few of the things. So you can go to your virtual machine and move to the workshop directory. So I'll be doing that here, so you can see where we're going, assuming I can keep up with my virtual machine. It's rather slow. What is happening? All right, so you can go to $workshop, which will take you to this GlueX workshops, physics workshop, and then go to session 3B. Okay, and there we have this macro called run deselector. So this run deselector is just a macro to make it simpler to actually execute these deselector commands that Paul was talking about before. So to run the deselector, you need to load this library, and so inside root you can just use this process line, and it executes this loading of the deselector. So that brings in all the analysis libraries, and you don't have to type that on the command line every time.
Is that selector in this directory?
Yeah, if you go to session 3B, so go to $workshop.
Right, I think I am.
Okay. Then there's session 3B. There should be several files.
Okay, sorry.
So there's a workshop data and a workshop, and so the workshop data has the separate data files that we'll be analyzing. Okay, so if you're in session 3B, we have this run deselector, which is loading the libraries we need. It's finding a file, which is at this path, the $data session 3B, and it's making this t-string for the file name, so that's just what the name of the file is. And we'll start first by looking at this SIM1 sample. So this string for the sample name is SIM1. And then we're using proof, where the command that Paul was talking about before was using this dProofLight Manager process tree, but you can also use things called a T-chain in root. So this T-chain, you specify the name of what the T-tree is, and then you can add files to it. So this is nice when you have, for example, a root file or a tree file for every one of the EVIO files in a run. You can add them all to this chain, and it processes them at one time instead of running a separate process for every file. So the command or the command line or the option to actually process these events, you load this chain, the name of the macro that you'd like to run, which is also in this directory called dselector p3py workshop, and then specify the output histogram file, an output tree file, which we'll talk about later, and then an options string, which is this options variable that we'll come back to. So let's just run that on the command line. You can do root -b -q, run dselector, and then specify the name of the sample, which is sim1. Okay, and so this is going to run the same process that Paul was talking about at the end of the last session. Where it's compiling this code, this dselector, and actually looking at and processing all the events there. So let's take another closer look at that dselector code that we're using. So we'll see how fast we can actually process events here. All right, so it started processing this little scroll bar. When you're running in batch mode, proof will give you a little scroll bar to tell you what percentage it's finished instead of bringing up this speedometer to tell you how fast it's moving through processing the events. Okay, so in the dselector, Paul took us through. Wow, this is really not going very fast. All right.
You want to use mine?
We could try. For some reasons, BlueJeans is not liking to play nicely with my virtual machine. Well, let's give it a shot here. Yeah, do you want to try to switch? Sorry, let me switch to using Paul's because I'm too slow.
Make sure we can pull up the website. Okay, got it. Where's your talk?
On the web page.
I just minimize it.
Okay, thanks.
And virtual machine is here.
Yep. Okay.
Power. Make sure we can share the screen. Down here. You guys see the desktop?
No,
It's not there. Weird.
There we go. Okay. Sorry about that. All right. Okay. So, right, so we're in this session 3B, and we're running this deselector. So that's deselector. So that's going to launch this process, which is running all of these, processing these events, and the actual, let's see if we can open this here. Yep. That's the wrong one. Right, so we're running over all these events inside the deselector. This is giving you a progress bar for how that's going. But what we'll need to do is actually separate the signal events in this this sample from the background events. So SIM1 includes both background and signal, and what we'll see is that after we process this SIM1 sample, we'll have some omega events that are actually inside the sample, and so we'll need to remove those. So the way that you do that is inside the deselector. And so once we get there, inside the deselector, we have these options for adjusting. I'll change the size here.
Just hit the plus to just maximize it. It's probably fastest.
Okay. We have an option for how we. There's some code that's commented out inside the deselector. So rather than writing from scratch, we'll actually uncomment some of this code. And so the place that that we'll see this is that there's an option to check what the thrown topology was in the BGGen sample. So once that's done, this SIM1 is finished, we can look at the histogram file that was made there. That's this hist omega SIM1, and look at the 3-pion mass. And so this is what that looks like. And you see that we do have this omega signal inside this BGGen sample. And because we have a separate generator which is already generating these omega events, we need to remove that from the BGGen sample. And so the way you do that is by commenting out this code here, which will check if the event had the thrown topology. So was it omega decaying to 3 pions? And then also check this option, this D option, what event sample it was. So we don't want to reject the omega events from the omega signal generator, but just the background sample. And so you, with both of those, you then skip the events in the BGGen sample that are of this omega topology. So once we have those, we have that set, we can now run this process again for SIM1. And it will again loop over those files, and we'll see that those omega events are removed from the BGGen sample. So just a word of caution here is you're generating a separate signal sample from this this Pythia background. You need to make sure that you're not double counting events or real signal events coming from the background sample. So that's what that looks like, and at the same time we can move on to the next thing. So that was kind of the first step where we saw that in the BGGen sample we have these omega events, and we need to get rid of those for this omega analysis. So we're going to process both of these samples, the sim1 and this angle sample, which is the omega signal, and then take a look at those for the next step in the exercise. So it should take a minute or so to run through this, and we'll look at that. So let's see, the next thing, while that's running, we can check. So this is just a bit about how you actually do that. As we looked at in the deselector code, the place where you specify the option is in this run deselector. So we looked at this earlier, but you can change the way that you can specify this string options and pass that as an option to this process chain. And that allows you to do different things for different samples. So for this sim1 sample, we pass the string for the sample, which is called sim1, and then inside the deselector, we check whether the sample was actually sim1 or not. And that way we're not rejecting the real signal from sim1. So that's a way of treating two different samples differently inside the deselector without having to recompile what's going on there. All right, so let's take a look at this. Sample again and open a T browser, and we'll see that now we've removed these omega events. There's no longer omega events in this pggen sample. Okay, and so yeah, just more information about where you actually set that in the process chain. So next, we have this removed, and we see that's gone. And so what you can do after you've created these two samples, so we'll also process this angles sample, which is the omega sample. And that'll create another histogram file for the signal sample. And so now we'll have, in this directory, we'll have two histogram files. One is the sim1, which is the background now, since we've removed all the signal, and the other is this angle sample, which is the omega signal that we're looking for. So once that's finished, we want to actually fit that and take a look at what the omega signal looks like for both of those samples. So there's a macro there called hist fit omega, and you can run that and get a plot for what the distributions look like after applying just very minimal cuts. So the only things we've applied here are that the kinematic fit converges, no particle identification cuts or other things, and so we can see that for these two samples we have in blue is the, let's see, I can go here to get a better picture. So in blue is the omega signal sample that we're calling angles, which has this the right angular distributions. BGGen is the background, which doesn't have the omega, and the total is in black. And so you can see the fit is not doing great here because we have a lot of background. We haven't applied other selection cuts yet. But at the moment we're fitting this with this Avoidtian with a linear background. And so you can do that by just fitting this full black histogram. But then you want to actually study this and evaluate what your purity and efficiency are. And so by having this sample of pure signal and a sample of the background, you can estimate what your efficiency and purity is just by integrating under the curve for these two different samples. And so at this point, it's not very good, but by the end, as we saw from Paul earlier, once we apply particle ID and kinematic fit cuts, we can get a pretty pure sample. So a little bit about what you want to think about in event selection. For each analysis, we'll need to strike a balance between objectives of having a high efficiency and high purity, and that really depends on the specifics of your measurement. So for this case, we're looking at the omega spin density matrix elements, where I think our high priority is having a high purity. So with a large signal cross-section like the omega, statistics are not really limited, and so we can afford to make maybe some tighter cuts, which can give us a high purity. And we're fitting, as we'll see in Mike's talk, these multi-dimensional angular distributions where the background could have some complicated shape. And so If it's difficult to understand the shape of the background in those distributions, then it's usually better to have a higher purity for those samples. But the ideal thing is as people are starting to look at analyzing data, to really be having a sample like this of signal where you know what the omega events are, and a background sample like this Pythia-based BGGen, so that you can do the parallel analysis of data and Monte Carlo at the same time and really evaluate how your efficiencies are changing and see that you're not throwing away events that you really like to see. So some typical cuts that Paul already talked about are particle ID and kinematic fit, and I thought we could just go through how we're actually doing those inside these D selectors for the root analysis. Paul mentioned these histogram actions and cut actions, which I think, Mark, you were asking where those are. These are located in this root analysis home libraries in the D selector. So I won't go through those in too much detail, but we'll look at the output that comes from those and how you could modify them later. So let's go back to the D selector code, and we'll look at where we can uncomment some of the options to actually fill those histograms and look at those. So we have these histogram actions which you initialize in the init function of this deselector. So some of them are just histogramming particle combo, kinematics, particle ID information. But you can specify whether you want to actually look at the kinematic fit quantities or the measured quantities. And so, for example, for the particle ID here, I have two of these histogram actions. One of them has a false flag, which means use the measured data. And another one has a true flag, which says use the kinematic fit quantities when you histogram the particle ID. So when you're looking at beta versus momentum, you can decide how you want to calculate that momentum. Then there's also these cut actions, or there's an example here of a cut action, which is using the particle ID information that we're histogramming here. You can make a cut on things like the delta T plots that Paul was looking at before. So let's take a look at what those look at for one of these histograms. So for this, let's look at maybe the angles sample first. So this is the signal. And again, this is really, as we mentioned, doing similar things as what can be done inside JANA, but at the T-tree analysis stage, mostly for speed improvements. So for looking at, for example, the pions from the omega, we have these delta T variables, which for each of the different detector systems show what this delta T variable looks like. So for the time of flight, you see in the signal, we should have really a pretty pure sample of pions here. And so we have a nice peak right around 0.
Can you pull that up full screen?
Yeah.
With the plus.
And so that tells you that you can make a pretty tight cut here on this delta T and select the signal that you'd like. And then we can also look at this for the protons, for example. The different detector systems have different resolutions, and so you can apply different cuts on the delta T quantities for the different detectors. So, for example, in the BCal, at least in this simulation sample, there's some shift from the nominal 0, and so we've left the cuts pretty wide at plus or minus 2 nanoseconds to select these, but that actually looks better in the data than it does in the Monte Carlo.
And this Monte Carlo is 3 months old.
Yeah.
So it might even look better than Monte Carlo if you were generating new Monte Carlo.
Right. So the idea of these cut actions is that rather than actually having to go through and set a separate cut on that delta T for all the different particles, you can specify here a one cut to cut on all this delta T values for all the particles in your reaction. Yeah,
Is there a difference between D histogram action and PID D cut action? Because in your cut action you have true as measured data, but in your histogram action you have true as the kinematic fit data.
That's probably left over from we changed what the definition of true and false was
Okay.
just before this started, or
So
before
the comment is wrong, the code is
yeah.
correct.
Okay.
This is, yeah, false is measured. Okay, so, right, so for here, we're using this combo, and then we're making, the flag tells you whether you use true or false for measured or kinematic fit, and then a cut on the plus or minus delta t in nanoseconds. And then here you can specify which particles in your combo you want to actually make this delta t cut for, and then which detector systems. So you could add another particle ID delta t cut, which only cut on the protons in the bcal, and that would do a separate cut. So where you specify that is down in the process function, where you're looping over these particle combos. So I'll uncomment these cut actions, and so when you call this dpid delta t perform action, it's going through and calculating the delta t and checking whether it passes your 2 nanosecond cut on delta t. And if it returns true here, then you will keep that event, but otherwise you'll reject it, and so skip that event, that combo inside your event. The other thing that's true here is that you'll notice that when we're skipping a combo, we're also setting this flag here. So inside the tree, there's a flag that says whether the combo in that event is cut or not. And so if you want to skip that combo in a later step in the analysis, you want to set that equal to true. And that'll come up later when we're writing out the root trees that we need for the further analysis. You want to keep this flag to reject that combo when you're processing the events later on. So you can make cuts here based on the delta t with these generic cut actions, but you can also do things like histogram the proton DEDX in the CDC. And so here we're just from the particle combo wrapper, or for the proton wrapper, you can get this quantity for the DEDX and make that plot. So that shows up, the same plot shows up here in the particle ID, where you can look at the DEDX and the CDC, but then you can, this is just an example of how you make that plot for sort of by, oh yeah, it was turned off when I ran this the first time. You can make that plot separately for inside your event loop. So let's go ahead, and now that we've turned on these particle ID cuts, you can do this in your version of the code as well, and then run these two samples again through the deselector. So you've made these cuts to turn on the particle ID cuts, and then we can look at what the effects are in our two samples. So those are making cuts. The two different cuts are on the delta t, and then also on the DEDX. So let's see, I'll run this on the sim1 while we're looking. So the DEDX cut is a curve that goes below the DEDX band. And so if I open another terminal, we can look at what defines that cut. Paul already showed that in the JANA event selection stage. So we have a function which these functions which define the minimum proton DEDX, which is just a functional form that goes below the proton band in the DEDX plot. So let's take a look at that again. So this function just goes and defines the curve that goes below this proton band. And so we're making those cuts, and after we process things, we'll run again this hist omega fit and see how we improved our purity with applying these different PID cuts.
Is the DEDX band done automatically, or is it humans that look at it and determine we're okay as long as nothing shifts in the calibration?
At the moment, it's a human by eye, because it's actually not the same, exactly the same in Monte Carlo and data, and it actually is, the calibrations are not quite great enough yet that it stays constant throughout time in the data. So it's still a work in progress there. Eventually, as Paul was mentioning, you'd like to do some confidence level type cuts on these once we've got things working expected. Right, so now we run this hist-omega fit again, and we can see that our signal is not diminished very much, but we've reduced our background pretty significantly with these particle ID cuts, and that's made some pretty good gains. And so what we're doing here is at the same time we're just checking the yield, and then what fraction of that is from the signal and what fraction of that is coming from the BGGen background events. And so this is a way of monitoring the purity and the efficiency as you're changing the different cuts. So we've gone through, so these were the exercises we just did, was to look at some of these PID cuts and the histogram actions and custom histograms, and then run the deselector with those to look at the results. Okay, so then just adding another comment about the kinematic fit. We've talked some about that already at the JANA stage. So one sort of an extra comment. So in the deselector, I'm filling two histograms. One is the kinematic fit confidence level, and the other is the chi-squared for the kinematic fit, chi-squared per degree of freedom. So those are here, where you can, inside the deselector, get from the combo this chi-squared for the kinematic fit, and then the confidence level. And so those are both filling the histograms there. And so sometimes, just to give you an idea of how this is calculated, the confidence level for the kinematic fit is just a probability for a chi-squared with a given number of degrees of freedom. So ideally, if the errors are Gaussian and the covariance matrix is accurate, then a 10% cut in the confidence level, so a cut at 0.1 here, is really a 90% efficient cut for the signal. And so the signal should be uniform in this confidence level distribution. But the chi-squared peaks at small chi-squareds for the signal. And so if these assumptions are not exactly true, then making a cut at 10% is not necessarily a 10% reduction in the signal. And so I find it sort of insightful to actually look at this chi-squared distribution as well, because sometimes when you look at just it's hard to see the signal in the uniform distribution than looking at the chi-squared. So what we've used in the event processor is a cut, as Paul mentioned, at 5 sigma, this 5 times 10 to the minus 7 cut here. So you can define these values for the different cuts for the kinematic fit, and then process again. So we'll run
the other terminal.
Yep. So we'll process those again and see how much more purity we can get from our sample. But really determining where we want to put that cut on the kinematic fit confidence level is sort of an optimization at this moment until I think those errors are sort of fully worked out to get your highest purity. All right, so while that's running, we can take a look at what the results will be. And so after we apply this cut on the kinematic fit confidence level at this plus or minus 5 sigma, we get a nice reduction in the background, which obviously this was what you probably should have started with, but so we could discuss the different elements of the selection. I thought we'd go over it in a little more detail. So we have this nice signal sample for the omega. You can even see some phi peak coming in here. These are real 3 pion events, but not the omega signal from this sample in blue. and so they're showing up as our background for the omega. And so after these selection cuts, we're at about 99% purity inside the omega peak, and the efficiency is almost 25%. So that's including all of the reconstruction of the different tracks and showers and the selection cuts that we applied here. All right. So,
So
yeah.
why isn't there more background? I guess, don't you have the BGGen in here?
Yeah, so this red sample here is what's left of BGGen after you apply these cuts.
And so this is Pythia modeling what's happening up at these energies, and maybe that's not perfect, but
it's not a lot. It's just the feedback.
well, there could be 3 pi events that aren't omega, or
Right.
Isn't there a 3 pi background that
Right. There should be some non-resonant 3 pi background that goes underneath there that apparently is not in Pythia very strongly. So yeah. So that's another word of caution that as you're doing these analyses with BGGen, it's useful to look at the backgrounds and try to decompose what the different elements of the background are. But it's probably not an accurate description of what we actually see in the data.
I'm surprised that there isn't more of 3 pi. I mean, 3 pions should be.
Well, I think even in the data, I mean, Mike has looked at this sum, and it's pretty clean under the omega peak.
That's great.
I think it's just like the cross section for the omega is so compared to whatever happens in maybe if you go to especially if you're energies, if you go to higher varying mass.
Okay. So any other questions on event selection? Yeah.
And just from the beginning, how did you determine how much of the background sample you need and how much of this?
Right. So to get the scaling between the two, you need to know what the cross section was for your signal sample. So there's been measurements of the omega cross section at these energies. And we also, BGGen has a total photo production cross-section of about 120 microbarns. So with those two numbers and counting how many events you generated, you can scale the samples to match each other. So that's how it was done. All right. So the last thing we need to do is once we've selected this sample of pure omega events, we need a way to propagate this to the next level of the analysis. So all we've done so far in the deselector is to make some histograms of different things with cuts. But you'd really like to get these events into a format that they can be used for some more complicated fitting, like Mike will talk about next, to extract these spin density matrix elements. So what we want to do is make a copy of this T-tree which only includes the events or the combos from the events that passed all of our cuts. So as I mentioned before in the deselector, we have this flag in the combos which tell you whether the event was cut or not. And so if I go back to the deselector again, kill it. You can see that every time I'm making some cut, so the continue here in the continue in to skip over the combo, I'm also making setting this value to true for this is combo cut. And so by doing that, you're setting the flag inside the tree to reject that combo. And then at the end here, we have an example for how to create the copy of this tree, which checks that flag. So what you do is for each event, you start by saying the event should be rejected unless otherwise specified. And then you loop over these combos. So this is a second loop over the combos, not the one where you're actually determining which ones pass, but you're checking if you're checking if this combo is cut or not for each of those events. And then if one of the combos passes all of your cuts, then you set this value for that event to false. And so if that event passes all of your cuts, you fill this output tree. And so what that does is writing a new copy of this tree, which has a much smaller number of events inside of it, and only the combinations that pass all of your cuts.
Not quite. It saves all of the combos, but the ones that failed your cuts will have that thing marked as, hey, I failed a cut.
That's true, yeah.
So all the combos will be in there, but you can check to see if you cut it earlier or not via this flag. This is combo
Right.
cut.
So it's writing copies of the events inside the tree, which include the combos that passed and didn't pass.
Right.
But as we'll hear about later, there's a script which takes these root trees and parses them and only keeps the combos that have this value set as false into the new format, which is used for the fit. And so the output from this can be used to directly go into that new format for the fitting.
At that point, there was still a possibility that several combos are saved.
That's
per
right.
Event, let's say.
Yeah.
Survive all cuts.
Yeah, so we haven't done anything here which specifies that we only have one combo per event. So there could be multiple combos inside here.
You referred to the speed up of this over the Jana plugin. How does that actually work? Where does the speed improvement come from?
Well, several things. First of all, you don't have to create the combinations. They're already done. You don't need a kinematic fit again. It's already done. And everything is stored in arrays in the file. It's much faster to just loop through arrays for the T-tree than it is to do things in Jana. But that's much faster this one.
Okay, so once we specify that, then we can go back and look at the deselector where we've specified this T-tree, this output tree file name, and this is the new root file which will be filled with these events that have combos passing all of our cuts. And so for this selection in the deselector, we'll make cuts. The full cuts are specified in here, where we make these particle ID cuts on DEDX and the time of flight information. We'll make a cut on the beam energy, so we're selecting only events in the coherent peak because that's what we want to fit for the polarized spin density matrix elements. And then finally a cut on the omega invariant mass. And so we'll the events that are passing all these cuts will then go into our root tree, which Mike will use later to do the fit to extract the spin density matrix elements. So with that, I think we've covered event selection. Any other questions?
Could you run it just to show how much smaller the tree is?
Yeah.
Started with?
So we can run the sample, and it'll make so these tree files are what's being created as we process these events. We started out with a file that was 600 megabytes for this Sim1, and when it gets done, I think it's only 10 megabytes maybe, because we're really rejecting all of these events from the sample.
Right, so even though the tree format has a lot of stuff in it, once you cut everything out you don't want, you'll still end up with a small file.
Right. And it gets even smaller once you strip out all of the detailed information and just have what you need for the fit inside AmpTools.
For the conversion of the tree, are you doing that or is Mike?
Mike. All right, so this is finishing, and this processing, as Paul was mentioning, goes faster when you have multiple threads, so you can speed things up, improve. Yeah, so this sample that was 800 or 600 megabytes is now down to much less than a megabyte once you've thrown away all these events. And so we've really reduced this tree. You can see there's only, for the background, we have a very small number of events that are actually passing all of our cuts. And so we get a pretty small file size at the end.
Look at non-combos just to see what it is. It's further down. Just further down still. Further down still. Oh, not that far. Stop. So when you do have background, sometimes there's a fair amount.
But then this is combo cut is the flag that we were setting.
Right.
And so this true value for is combo cut is saying that even though we have 34 events in this file, most of them have more than one combo, but this is combo cut is telling us that almost all of those will be rejected from our fit and amp tools because we've set this flag as to cut those events for the final analysis. And so this is what you're setting when you do this is combo cut flag to true.
It looks like the number with the true is the exact same as the number of events in the tree.
Yeah, I think. Let's see. So there's 35 events that have is combo cut false, and we have 34 combos or 34 events. So
right. So there's one event with two combos.
One event has two combos in it. Yeah. So it's a pretty small amount of double counting.
Does anyone have questions for Justin? All right, so we're ending the session a little early. Certainly, we have a coffee break. What's the schedule say for when we come back? Does anybody have that?
Yeah. So it's in half an hour.
Sean.
Okay.
So half-hour coffee.
So half-hour break. Certainly, if you want to work on, just play around with the trees. You want to take a look at them, and if you have questions, we'll be around and we can help. But we're due back at 10:50.
So this is from Monte Carlo Pythia data, whole mega analysis.
Well, there's this BDGen sample, which is the Monte Carlo Pythia, and then there's a separate sample of just omega events.
Right. Okay. Which says generated.
It's generated just for this signal sample, and Mike's going to talk about the generation of that.
Okay. How many did you generate for the signal and background? You did 3, was it the 3 million? Did you use all 3 million of those for this example?
Yeah, so there's 3.75 million events inside.
375 million.
Yeah. Well, there's 375 million in all of Sim1, but we're using 1% of that in our in this stage of the analysis.
Okay, yeah, because I was surprised that you only used 35 events.
Well,
at the end.
that's because it's coming from this plot. So it's the background. The BTGen sample is only 35 events in red here.
Oh god, okay. I thought those were your omega.
Well,
sorry.
Yeah.
All
So
right.
the omega is a separate sample which
I'm
has.
sorry. I thought you just ran those cuts over your signal one more time, and you were left at 34. I was like, wow, that's really
No,
crappy.
yeah, sorry, yeah. So the efficiency is actually pretty high for these real omega events.
Great, okay.
And it's the background sample that's small.
Very good. And all of these, so when you do this fit, you're doing this while you're running over your proof light. And you just like wrote that in your run selector code?
Well, no, the to make these fits. you
Yeah,
mean?
to like do these
Yeah.
fits, because I'm
this
trying to
is-
figure out how to do that like multi-threaded.
Well, the fit is this extra hist fit omega, which looks at it takes
Yeah,
the.
yes, you should.
So let's look at hist fit omega.
Technically, you don't have to, but it automatically sets up a bunch of things for you.
That opens the two histogram files that are the output here.
Oh,
One
so this
one
is
the
called
background.
when you've already done the cuts.
Yeah. So once
Okay.
you've already run the selector,
Yeah,
then
one
you
of the
open
things-
these two and make the plot.
Okay, so that's the only way you can do it is post facto because, yeah, I was trying to figure out how to do this with my, I really enjoy doing these multi-threading. And I thought, well, maybe after everything's merged at the very end, I can call this fit, but I guess this is probably.
There is a mechanism.
I probably
at the-
shouldn't do that.
At the end of truth, there is a mechanism to do like finalize.
Yeah.
And there it says, take the two histograms that are made and actually make a plot of it. Usually, it's better to make that a separate step, and so just skip that.
Okay. And all of this is going to be saved onto the virtual machine in the directory that we were just in?
Yeah.
Okay, yeah. Well, I'll just take a look at your code then and just kind of go on the same method.
Okay.
First of all, we have to, what we got here somewhere. So that takes.
Yeah, please do. Actually, let me stop recording before we